Okay. So what did we get for the answer for the first exercise? The solution, what did we get? 3? Okay. For 1A, we got 3? 4. Okay. So after we do our work here, we get x equals 4. And what did we get for this one? X equals 3. Oh, someone got a -3? Okay. You got -2. So we've got a couple of different answers. Okay, so let's go over this one. All right, so let's take a look. I'll erase all of this now, and let's do it together. So we're going to try something. I'm going to be the writer. Is everybody listening? I'm going to be the writer, which means I can't think and I can't talk. So that means you're all going to take turns telling me what to write. All right, so someone can start. They can do a little piece of it, and then someone else picks it up. It's kind of like a round robin. Okay, so someone want to start, and I'll just write what you tell me. Christopher? You want Chris or Christopher? Okay, Chris. Okay, you're done. Someone else? Katie? Yeah? Katie? Either one. Yeah? You're good? Okay. Everybody okay to there? Focus should be right here, folks. That's where the error tends to be made on this problem, is that people forget to change the sign for the second term. Okay, someone else want to continue? Hannah? You got to tell me how I got there. I can't do that in my head. So, oh, you see where you went wrong? Okay, good. Was it with the plus 20? Okay, good. So let's continue with this. Then someone else, yeah? Tom? Before we do that, is there anything else? I know I'm not supposed to talk. Is there anything else you want to do before you start? Katie? Okay. Combine like terms, you always want to, I guess I'm going to talk. You always want to make sure the expression on both sides of the equation is as simple as possible. It doesn't mean you couldn't add 5x right now. You absolutely could do that. But the tendency is that you could lose track of something unless you combine like terms. So usually you want to put the 10 and the 20 together first. It's not necessary, because if you had added the 5x to both sides, you would have been left with the 10 plus 20. Then you would have combined it. That's okay. It's just this tends to be the standard way. But, you know, you can be a little bit of a outlier if you want and do it a little different. Okay, so someone else from here? Nobody else from here wants to? Yeah, go ahead. You subtracted 3x from both sides, okay? And what did that leave you with? Okay, someone else want to help me from here? Then you subtract 30 from both sides, okay. And what's that leave you with, Drew? Okay, thanks. And anybody want to finish this off? Last step. Divide both sides by -8, and we get x equals 3. So x equals 3, we say, is the solution to that equation, because when you check it and you throw 3 back in for x, you'll get, what was it, 15 on one side and 15 on the other when you checked it? Okay. The book says every single equation, no matter what type of equation you have, and we're going to be looking at lots of different equations in this class, the answer is a set. And in this particular case, it's a set with one number. The solution set looks like this. Little curly braces with a 3 in the middle, and then little curly braces. So when you see my math lab, it's going to be asking you to put the answer in a little set formation like this. Okay. So over here for the first one, you'd just throw a 4 right in there. So the solution set to the first equation is the number 4, and the solution set for the second equation is the number 3. Okie doke. And the book will continue with that kind of notation throughout the entire book. Right. So the next thing we want to take a look at is if you all had graphing calculators at your seats right now, and if you have one, you can pull it out. It's not necessary, but if you have one, you might want to follow along. Is how could we solve this equation B using a graphing calculator? So that's kind of what we want to take a look at. So unfortunately, we already know the answer. We know the answer is 3. So what would this look like on our calculators? How would we actually go about taking an equation like this and using the calculator? Well, what your calculator does is it can give you a graphical solution. It can give you a picture of the solution if you know what to look for. And that's what we're going to take a look at in a minute. And you can also get a table, and you can find the answer sometimes in the table. Sometimes the table's not going to help you out because you may not have any idea where the answer is. We happen to know the answer is 3. So we're going to be able to, kind of zoom in on this table or hone in, and really find the answer. But sometimes this can be a little frustrating, the numeric check. All right, so if you have an equation like we just solved in B, what you do is you enter each side of the equation separately into the y1 equation and the y2 equation. So let's take a look at how we would do this on our calculator. So here's our calculator, and I hit my y equals button, and I take the expression on the left side of my calculator and I enter it just like I see it. I don't do any kind of simplification, just in case I might do something incorrectly. I just enter this exactly like I see it. So there's the left side of the equation. The right side is 10 take away 5 times the quantity x minus 4. Oh, I put it in the same place. Ooh, so now I got to do it all over. All right, 3 times x plus 2, and go down to the next equation. 10 take away 5 times x minus 4. All right. So there's my equation. I've put it into y1 and y2. So if I want to use the table, what would I do? I would just have to start somewhere. And again, when you don't know what the solution is, this is the tricky part. We know it's 3. So we're just going to say, well, let me start my table, say, with -10. We'll just start there. We'll have an increment by 1. You could have an increment by 0.125, 0.1, 0.2, anything you want. And again, if you had a really funky answer, you might not be able to find it in the table. So we'll just do 1. And we're going to keep the values of x automatic and the values of y automatic. So it's just going to go ahead. It's going to throw in -10 into this equation and calculate the value for y1, and it's going to throw -10 into this equation and calculate the value of y2. So let's just do that once to see what we should expect in the calculator. So if we put in -10 for x, what is y1 going to be? Y1 is going to be 3 times -10 plus 2. Y1 is going to be 3 times -8, which gives me a -24. So the value that goes along with -10 on my first graph will be 24. So on my first graph, the point, the ordered pair, -10, 24, I would put a little dot. That would be my first point on my first graph. What about my second graph? My second graph would have 10 take away 5 times -10 minus 4. And that would be 10 minus 5 times a -14. And -5 times -14 is 70. So The value there would be 80. So my second point on my first point on my second graph would be negative 10, 80. So would negative 10 be a solution to that equation? Yes or no? And how do you know? So you guessed yes. And why do you say that, Adriana? Okay. Well, let's take a look at what we would have done back here for a second. If I plugged the answer here, 3, up here, I would have gotten a number, right? And I put the number 3 here, I would have gotten a number. And what would have to be true about the number that you got on this side and the number on this side for this to be the solution? They'd have to be equal, right? So now we're calling this side y1 and this side y2, okay? So is that going to be the solution? So I'm really glad you said that because it gave us a chance to look back and see what to expect, right? So what we need to be looking for, folks, is the value of x that makes, remember, this is just the left side of your equation and this is the right side. So to be a solution, these two have to be equal, right? So let's take a look at that table again and let's see if we can find it. Like I say, sometimes you can and sometimes you can't. So here's what we just got. Oops. Oh, I didn't write negative 24 here. Okay. So at negative 10, we got negative 2480, and we're scooting along here. Not equal, not equal, not equal, not equal. And you keep going. Not equal, not equal. I'm starting to feel like I'll never get there. Oh, there we go. There it is, right there, right? Right there. At x equals 3, the left side of the equation equals the right side of the equation. All right, so that's how you would use your table to actually find the solution on your graphing calculator. So I'm just going to superimpose this right over our table here. So this is the kind of thing you're going to see on your homework. They're going to say, they'd give you a picture like this and they'd say, find the solution to the equation. And the way you do that is you find the row where y1 equals y2. So the solution is, this is your solution. And what this means is that you have you have 1 point on each of those graphs, and that point is the point 3. When x is 3, y is 15 for both of them. y1 is 15 and y2 is 15. Okay, so what would this look like on a graph if you were to graph it? Well, first of all, what kind of graph do I get when I graph 3 times the quantity x plus 2? What kind of picture would I get? Yeah, Katie? Linear, I get a straight line, yeah? And what do we know about that straight line? Well, let's see. y1 equals 3x plus 6. So what could you tell me about that straight line if I would just do a quick graph of it? Yeah, Katie? It has a positive slope. What else can you tell me about it? It has a y-intercept of 6. So I'm going to do something like this. It's going to look something like that. Okay? I'm just doing a quick sketch. All right. Now let's take a look at y2. y2 is 10 take away 5x plus 20, which is 10 plus 20 is the 30. So y2 is going to look like this, minus 5x plus 30. So can someone tell me something about that line? Has a negative slope, and where does it go through the y-axis? At 30, so it's a lot further up here. So I got to like really scoot this up here, right? And here's a 30, 0, 30, and my slope is negative. All right. So when I'm looking at something like that, where is the solution to y1 equaling y2? Where do I find the solution? Where they cross. Because where they cross, what's true about this point right here where they cross? That point, whatever it is, lies on both lines, so they both have the same x value, and their y values are equal. So the intersection point is going to turn out to be 315. 315 lies on both of those lines. If you put a 3 in here, 3 times 3 is 9, plus 6 is 15. That's definitely on the black line. And if you put a 3 in here, 5 times negative 3 is negative 15 plus 30. That's 15. So it's also on the blue line. So when you're using your graphing calculator and you're trying to find the solution to an equation, you graph the left side and the right side. The first thing you're going to hit is zoom 6. So let's take a look at what happens when I do zoom 6. Zoom 6. So there's my first equation, and there's my second equation. What's the problem? Yeah, zoom 6 is standard. So what's the problem right now with that picture? Yeah? Yeah, I have to adjust it because what can't I see? Yeah, I can't see you can't see the whole graph, or basically you can't see where the two lines are intersecting, right? So let's pull this out and put it down here in our notes. So this is with the standard window. And the problem here is we have to adjust, Sam says we have to adjust our Y max value so we can see the intersection point. Okay, so let's do that. That's no problem. We actually know that we've got to go higher than, what's the maximum right here for our Y value with our standard window? What was the biggest Y could be? 10, right? So let's make it a little higher. Again, without knowing the solution, you wouldn't know how high to go. So it's really just a judgment call. I'm just going to go up to like 50. Hopefully I'll get it when I do 50. Then you hit your graph again, and there's your first line, and there's your second line. Now you have to find your intersection point. So let's do this. We'll get the right window now. And just a little review for you. I take this window and I want to talk about how to say what the actual X-min, X-max, and Y-min and Y-max is. How do I notate that? The window is, remember you put the brackets, the X values first, negative 10 to positive 10, increments of 1, Y, and what were the Y values? They started at negative 10 and they went up to 50, and those were by 1. So that's the window that we have, and there's our intersection point. The intersection point, the X value of the intersection is going to be the solution. Okay, so this is going to be X, Y1 and X, Y2. It's the same X value for both the line that's defined by Y1 and the line defined by Y2. So let's find that intersection point. So we go back to our graphing calculator, and now to find the intersection point, it's actually, you could do trace, but that could take you a little while, Jesse, to try to like get it exactly. So there's actually a nice way. You hit second trace, which is your calc button. And guess what? When you hit that second trace, look at what you can do here. You can calculate the intersection. So you go down to intersect. Yeah, it saves a lot of time. Intersect. You hit that, enter. And you could just play around with this and get it really close, like just kind of getting it close like that and saying enter. And then you could get it a little bit to the right of it, or you could scoot up there somewhere and hit enter and then enter again. Oh, come on. Second. Oh, I'm not on the second curve because I'm going to show you a fast way. I never use this method. That's why I'm not so quick here. All right. Now let's come down. Yeah. On that second curve. Here we go. Hit enter. Then the guess is a guess. You just always hit enter. And there's your intersection point. X equals 3, X equals 15. So let's put that in the lectures. Here we go. So that shows you the solution here is X is 3 because it makes both Y values the same. All right. So what's the fast way of doing that without even having to do all that work? The fast way is this. So you go up to second trace. Let's go here, second calc. Go down and say intersect, and this is really great. All you do is go enter, enter, enter. Voila, there's your answer. You don't even have to move that cursor about at all. Enter, 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 boom, it pops up. William, do you have a question? Okay. Did I see a hand or am I imagining a hand? I thought I saw a hand. All right. Any questions on finding the solution to an equation using the graphing calculator? Anything at all? Okay, so you'll have some stuff on my math lab, but like I say, they'll either give you a table like this, or they may give you a picture like this and ask with the information like this. They'll give you this and they'll say, okay, what's the solution to the equation? Okay, so you'll get like the output of the calculator versus having to actually do it. All right, so if we look at today's topic, it's called linear and rational equations. So what we did in number 1, we solved linear equations. What does a rational equation look like? What do you think a rational equation is going to look like based on the name rational equation? Any guesses? Whole numbers. Well, these have whole numbers in them, and it's called linear. Let me just say this. These are not, well, I shouldn't say, they are some linear, let's say the rational equation would be the big, well, let's see, linear equations would be the big umbrella, and these would be, I guess you could call everything a rational equation, but I'm just trying to get at us why these are not what we're going to be looking at. Rational has the word ratio, which you think of fractions, right? So we want to be able to solve fractional equations. Yuck, yuck, yuck. Ugh, ugh, ugh. All right. Here's a fractional equation. This is linear. See, this is a linear equation because the highest power you see x raised to is the first power, right? It's linear. But it's a fractional equation or a rational equation because your denominators are different than do not have 1. But technically, I could still say the first one was considered a rational equation as well. It's just that these we treat a little differently than we would 1A and 1B. When I asked those of you who got a chance to solve this, what would be the first thing you would do if you were going to try to solve this? I want to give everybody a chance to look at this because some of you were able to get to number 3 and some of you weren't. So I want to give you like a minute or so to look at this. And then I'm just going to elicit responses. Try not to look at the grid below it, the table where I talk to you about how to solve it. Just what would be your first, write down your first idea of how you would go about solving something like this. What your first steps might be. So what might be your first steps? I want to hear different people's responses. Okay, so anybody can, so for your very first steps, notice I have that as plural. So find a least common denominator, okay. Do you mind if I say LCD there? Okay. Other ideas? What about after you find the least common denominator? Yeah, Christopher? Okay, so you've decided it's 12, okay. Yeah, I agree. Okay, so first of all, you want to take this first, the left side of this equation, and what you want to make it into, you want to do something over 12, right? Okay, right. So then what you're saying is you would take each part of that equation and turn it into an equivalent fraction that has 12 in the denominator, right? Okay. And we know we would do that by multiplying this fraction by some form of 1, because we can multiply anything by 1 without changing it. And in this case, it would be 3 over 3. Okay. So we'd have to do that with each of these particular pieces. And we would do that. Okay. When we do that, we're going to get this. I think, if I did it right. Okay, you don't have to copy all this down because this isn't what I want to do today. I just want to say this is the typical response or the expected response. This is where 99% of students, this is how you would approach it. So just watch. This is all I want you to do. This is the really interesting time now. Students get here. They get here. They do all of this incredible algebra, and then they don't know what to do once they get here. So suppose you went ahead and did all this great algebra, and you got to there. What is your goal? Tell me what your goal is. To find x, so what? To find x to make what? It's a solution, and so that means so that this, the left side equals the right side, right? Can you tell me anything right now on the left side and right side that's already equal? The denominator, they're both 12. That's irrelevant. The 12 right now has no say in the solution. It's gone. These are already equal. You can go right like that. Is that an easy equation to solve? 3x plus 3 equals 10 minus 4x? So what's heartbreaking for me is I see students do all this work, they get to something like this, and then they stop. It's like they just stop. Their mind can't even process this. They're like, what do I do now? Well, if I gave you this, if I gave you that problem, you'd say, this is just 3x plus 3 over 10 minus 4x. My denominators are the same. I only have to pay attention to making my two numerators equal. It's the same when it's 12 down there. I could have smiley faces down there. It doesn't matter because they're equal. So one way to do it is to completely ignore the 12s and just set the left side, the numerator on the left side equal to the right side, or the part of your education that we talked about the other day that we have a really hard time recognizing is that this is an equation and it has a very special name. Does anybody remember what we call an equation that looks like that? All right, so we're going to play, it's football season, right? So for once, I'm going to be like a cheerleader. Give me a P. Give me an R. You better get better if you're coming to my football game. Give me an O. And when you get it, let me know. Give me a P. P. Haven't heard it yet. Give me a O. Proportion, right? This is a proportion. So how would I go? If you do it this way, how could you solve this? What's that called, Katie? Cross products are equal. So this 12 times 3x plus 3, and this 12 times 10 minus 4x. And now I ask you, do you really need to, oops, I forgot my x here. Do you really need to distribute that 12 through? Couldn't I right now divide both sides by that constant 12 and get rid of it? Yeah. So you have a choice. You can make more work for yourself and distribute this on both sides, or you can just say, I'm getting rid of that 12. And lo and behold, guess what we get? 3x plus 3 equals 10 minus 4x. The 12 is irrelevant at this point. Totally irrelevant. Guess what? You could have done that right up here at this step. You could have said, oh, guess what? This is an equation. I have a very powerful tool when I'm trying to solve an equation. I can multiply both sides by any non-zero number I want. Voila! Back to my 3x plus 3 equals 10 minus 4x. So I've just shown you 3 ways to get out of your little problem when you solve an equation that looks like this. And now I'm going to tell you, hopefully you'll never get here. You'll never do it this way because you have an easier way to do this. The easier way is not to convert all of those individual terms to twelfths. Just get rid of all the denominators at step 1. And that's what I've tried to show you with this series of steps here. What? What? I'm going to... No, it's not cheating. It won't. It's going to explode if you try to convert everything to common denominators. No, I agree with numbers, it's really easy, Anna, but in a minute, they're going to look like this. Okay? You don't want to do all that converting when it's those kinds of things in the denominator. So believe me, I'm really trying to make life a little easier for you, even if sometimes you think I'm not, okay? All right, so let's start first with when we have denominators that are constants like this, 3, 4, and 6. So do you all agree it's easier to solve the equations like 1a and 1b that didn't have fractions in them, right? Didn't have denominators different than 1? And so we want to be able to create equations that have 1 in the denominator. We don't want 4s and 3s and 6s and x's and x plus 2s. So let's see how we can clear the equation of all the fractions. So here's our given equation. We want to find that common number that Christopher identified as the lowest common denominator. It has a different role. We're going to find that number 12. But instead of making all the denominators 12, we're going to say 12 is the common multiple of 3, 4, and 6. So it's a little different twist. We're going to use it differently. It has a different role, but it's exactly the same number. And let's do it the long way, even though you wouldn't do this with numbers, but I want you to see the relationship when we get to algebra. Yep. What are we doing? We're number 4. I explained how to do it if we converted everything to denominators of 12. This is a different method, yeah? One that I hope to convince you is easier. Sometimes I'm successful and sometimes I'm not. And you know what, folks? Here's what I want to tell you. If you always want to do this kind of thing, absolutely fine with me. I just want you to know how to finish solving it from here. That's why I showed you that. Because I know no matter how much and how enthusiastic I am about showing you this next method, many of you are still going to do this. And that's fine. I don't have any problem with it. I just don't want you getting stuck when you've done all this beautiful work and not be able to get to the answer. So here's another approach. All right. And I'm going to show you this because even though in our minds right now we can look at these 3 numbers and boom, we can come out with 12 as the common multiple, the process for doing that really in our heads, that our heads does, is it finds it by looking at the prime factors. And when these become things like x squared plus 5x plus 6 in the denominator, we've got to factor everything. So this is really what we do. We take each of these denominators, 4, 6, and 3, and we represent them as prime factors. Well, guess what? 3 is already prime, so there's nothing to do there. What would 6 be as represented as prime factors? Anna? 2, 3. You mean 2 times 3? Okay, thank you. 2, I'm being a wise guy. All right, 2 times 3. All right, there we go. And what about 4? How do I represent 4 as prime factored, Katie? 2 times 2. So do you notice here that I use 2 different colors? Which means to build this common multiple that we know the answer is 12, I only need 2 prime factors. That's it. Now the question is, how many 2s do I need and how many 3s do I need? I guarantee you, if you multiply 2 times 2 times 2 times 3 times 3, you'll get a multiple. Absolutely, 4 times 6 times 3 is a multiple, but it's not your smallest. So this is where the little idea of the little Venn diagrams I showed you came in. So to get 4, what do I need? I need a 2 times a 2. To get 6, what do I need? A 2 times a 3. So I'm going to borrow one of the 2's right here. I'm going to borrow that one, and I'm going to put my 3 in. So right now, what number do I have? 12. And I don't have to go any further because guess what? 3 is right there. So here's my lowest common denominator if I was going the route Christopher mentioned, or this would be my multiple, my lowest common multiple. So I can now multiply everything. Because I have an equation, I can multiply both sides by any non-zero quantity I want. And that's the key. If I cover this left side of the equation up and I told you to add 1/6 plus 2 minus x over 3, you'd have no other choice. You'd have to convert to common denominators in order to add. But with an equation, you have this very powerful tool here. You can multiply both sides by 12. So this is what I'm going to do. 12 times x plus 1 over 4 equals 12 times 1/6 plus 12 times 2 minus x over 3. There we go. This is legitimate. I'm not multiplying by 12 over 12. I'm multiplying by 12. But because I'm doing it to both sides, I keep this equation in perfect balance. Okay? Now, it's beautiful because the multiple you have chosen, each of these denominators are factors of that number. That's how you created it. So you've done a master manipulation here. You said, hey, I could have multiplied both sides of this equation by the number 15, but that's not going to help me with these particular denominators. But any number that that have this combination of factors or anything higher than that, 2 squared times 2 times 3, 2 cubed times 3, 2 cubed times 3 squared will be a multiple. So now, what do? How do you solve this before I distribute? Yeah? That's all I am going to multiply. I'm not multiplying the denominator because this is all sitting over 1. Doesn't matter because when I do this multiplication, it looks like this. When I multiply fractions, it's numerator times numerator and denominator times denominator. Okay? So, before I even move on to there, this is the golden part right here. 4 goes into 4 once, 4 goes into 12 3 times. How nice is that? Look at my denominator now, 1. 6 goes into 6 once, 6 goes into 12 twice. Beautiful. 3 goes into 3 once, 3 goes into 12 4 times. So what do I have now? 3 times x plus 1 equals 2 plus 4 times 2 minus x. If I gave you that equation at the beginning, you would have said, easy. When you look at this, you get a little bit of a panic in your stomach, right? So you can avoid all those fractions. And from here, you just go through the normal series of steps you would normally do. You would distribute here, 3x plus 3 equals 2 plus 8 minus 4x. 3x plus 3 equals 10 minus 4x. Add 4x to both sides and subtract 3 from both sides. You get that. X is 1. And you're all done. Okay? So I don't know if I've convinced you that it's easier, but it's the only way to do the series of problems that we're going to do next without lots of pain and agony. All right? Any questions on this? Yep, Katie? What dividing? You mean the fractions when I multiply that by 12? Okay. Okay, so this is where arithmetic, passing the arithmetic test is really critical. Okay, so what is the numerator on this again? Is it x plus 1? X plus 1 over 4, does everybody agree? Okay, and this is sitting over a 1, right? Do you agree that multiplication is commutative, that the order that I multiplied never matters? All right, so is there anything wrong with calling this this? Is that okay? Katie, I'm looking at Katie because does it matter where that 4 is? No, because it's times here, right? Or this is one big fraction. Do you agree I can write this, Katie? Okay. And do you agree now that I can scoot this right out all by itself and do this? Okay. And then what's 12 divided by 4? 3. And that's all you're doing when you do this, Katie. You're just reducing 12 over 4 to 3. Okie doke? All right. Any other questions before we move on? Because I want you to feel comfortable with why you're doing this and why it works, not just how to do it. Okay, so all of this is fraction stuff. And why not get our fraction stuff, because it's one of those stuffs in us, straightened before we move on. Any other fraction stuff? That darn fraction stuff that always kind of messes us up. All right, let's move on real quick here to some rational equations where the ones we just looked at were rational equations, but now they're going to look a little yuckier because they have algebraic expressions with variables in the denominator. But listen to me, the process is exactly the same as what we just did. So the one thing you have to be like fully cognizant of is now, don't forget, we can't have a solution to an equation that's going to make the denominator equal to 0. So before you even start your solving, you have to write what values of x are excluded from the solution set. So what are the excluded values when you look at this first equation? What are the excluded values when you look at this equation? 0. Because if you put a 0 in for x, this denominator is 0 and that's denominator 0. So this one is x cannot be 0. Okay, notice this second equation, everything is factored for you. This first factor is prime, the second factor is prime, and they already did this factorization for you. What are the excluded values here? Negative 2 is one of them, right? And plus 2, so plus and minus 2, right? Now, for this next one, you got to do a little work because the second denominator is not factored for you. The first denominator is factored, so what's an excluded value for this very first one? 0. X can't be 0. And now we have to factor this second denominator. How do we do that? How are we going to factor x squared minus x? The greatest common factor here is, what's common to both of them? X. When you pull that out, you have x minus 1 left. 5 is sitting over 1, so we don't have to worry about that. So we already have this factor as x equals 0. So what's going to make this factor equal to 0? Plus 1. So x cannot equal 0, and it can't equal 1. All right? So we are going to solve this equation as a class, and I'm going to leave these two for you to solve. So let's take a look at the third equation here, and we'll do it as a class. All right, so step number 1 is that you have to factor all denominators. You have to, so you can find what the excluded values are. So factor all denominators, and we just did that. So let's rewrite it. 1 over x plus 1 over x times the quantity x minus 1 equals 5. And I'm just going to put the 1 there just so we can see the numerator and denominator. Okay, so that's our first step. The second step, and if it's already factored, then this second step becomes your first step. So find your excluded values. And we just said our excluded values are x cannot be a 0 and x cannot be 1. So if we go through all this work and we get one of those answers, we have to throw it out. It's not good. Third step, Find the lowest common multiple. Well, you're in luck here, folks, because your second denominator, this is a multiple of that. It's the x minus 1 multiple. You've got two prime numbers here, or two prime factors. You've got this one, x, and you've got x minus 1. So if you were looking at the little Venn diagram, here's your first denominator, x. To get your second denominator, you grab that x and you multiply it by x minus 1. And there you go. That's your LCM. X times x minus 1. So you find the lowest common multiple, and next you multiply everything on both sides of the equation by x times x minus 1. And what I would suggest, if you're having trouble seeing that, how to reduce it, is just write one fraction bar. So for example, just do one fraction bar like this all the way across, just like that. And so you started out with 1 over x. Now you're multiplying it by x times x minus 1. Just throw everything in the numerator. X times x minus 1 times another 1 over x times x minus 1. And then 5 times x minus 1 over 1. So I've multiplied. I'm going to make the original equation. I'm going to put it in black. Here's my original equation. 1 over x, 1 over x times x minus 1, and then 5 over 1. So you can see all I did was multiply each of these original terms by the quantity. This red quantity goes in the numerator of every single one. So I think it's easier just to do one fraction bar, and then you don't have to worry what's canceling with what. Now you look at each one and you say, do I have a common factor in the numerator and denominator of this first one? Is there a common factor to both? Yeah, and that's a number 1. That's a foo-foo. And what is it, Jesse? X. Boom, that's gone. So what would this now become? 1 times x minus 1, which is x minus 1. Cool. That's pretty easy to look at. That doesn't hurt my eyes. And now I look at my second one. Do I have any common factors in my second one? What are they, Katie? X times x minus 1 in the top, x times x minus 1 in the bottom. And what's it leave me with? Nothing? 1. And that's another mistake people make. They think there's nothing there. But remember, we're finding a 1. And 1 times the 1 that's there is 1. And then finally, well, the next one, the denominator is already 1. So we have 5x times x minus 1. Right? Now you have this equation to solve. So let's do it. What's the left side reduced to? X take away 1 plus x. What's that become? X, because this just goes to 0. We get x. Now we have 5x times x minus 1. So I'm going to use my nice little distributive property. No negatives out front that I've got to worry about changing signs. And what do I get on the right side when I do that? 5x squared minus 5x. Okay. Now, what kind of equation is this? It's quadratic because it has that squared term there, quadratic equation. So to solve our quadratic equation, we set it equal to 0. So we subtract x from both sides to do that. I get a 0 on the left side. You don't just leave it blank and have a tippy. This has got to be a perfect equation, like on a seesaw. It's not just one person on the seesaw. 5x squared minus 6x. Now, in order to solve this, we factor the right side of the equation by finding the greatest common factor. And what is the greatest common factor here? X. So we pull the x out and we get 5x minus 6. And now we set each factor, we have 2 of them, set each factor equal to 0 and solve. So let's do that. So I set my first factor equal to 0. There's no work. X is 0. Fine. And what about my second factor when I set that equal to 0? I add 6 to both sides. I get 5x equals 6. and then I divide both sides by 5 and I get 6/5. Or 1, you could also call that 1.2 if you wanted. Doesn't matter, decimal or fraction, I don't care. Okay, and then you're done, you circle both of them, right? Because I'm trying to solve this equation right here, Isabel. And to solve this, it looks like this. A times B equals 0, because it's multiplication here, right? So if A times B equals 0, what do you know about A or B? One or both has to be 0. So we have to figure out what makes this 0 and what makes that 0. And then that would make this equation 0. So let's try it. If I put a 0 in here, Isabel, I get 0 times something. That's a 0, right? If I put 6/5 in here for x, 5 times 6/5 is 6. 6 take away 6 is 0. And 0 times 6/5 is 0. So that's, once we factor this, that helps us find the two solutions. No, yeah, you could check it, but I would always check it back in the original problem, because if you made any mistakes to get to here, right? Now, so my question is, do I just go like this, boom, boom, and I'm done? Why not? Because look back at your first step. What couldn't x equal? 0 or 1. So this cannot be a solution to this equation. So this equation has one element in its solution set, and it's just 6/5. There's only one solution here. Okay, so you have two more equations to do on your own. So try those. I'll check them out if you'd like, or you can check them with each other. And then let me know if you have any help by putting your flags up. And that's all we have to do for today. So finish up. What number are we on? I forgot what number we're on. 6. So do 6A and 6B. Yep, 6A and 6B. And if you finish that, you can look at the activity I gave you called working with resistance.